we did there. So in 1C3, we finished the first part of that example, which is to find what is the velocity and acceleration for the particle A, particle P, the same thing, at a certain angle. And how we did that is just using the given condition r and theta dot to construct our velocity and acceleration under polar coordinate system. And we have velocity and acceleration find out for this particle. Now the next question is to find the speed of this particle to determine if that speed is increasing, decreasing, or constant. Last time I asked you to make notes on this. If you see a question like that, that means to find what? Look at your notes. What's on your notes? V dot. If you see a question like that, means find V dot. Find the sign of V dot. If the sign is positive, speed is increasing. If the sign is negative, the speed is decreasing. 0, that's constant. So now today's task is to find out what is V dot for this particle. Okay. All right, to find V dot, we know V dot, the goal is to find V dot. V dot, it's inside path coordinate system, right? We know that. But what we have for this problem, all we know is in polar coordinate system. So that tells you we want to do conversion between polar and path. But there's a question, the big problem. We don't really know the angle between path coordinate system and this polar coordinate system. Previously, all the practice we did, I draw the both coordinate system. It tells you that's the angle between either I and ET, something like that. Then you do the conversion, build triangles, find cosine, sine, theta, stuff like that, right? Build conversion equations. But for this, we have no idea what's the angle between those two coordinate systems. This will be one of your homeworks. Your homework has a very similar problem set up. You don't know the angles between two coordinate systems. And today we're going to introduce 2 ways to do that. So first, for this problem, we're going to use a technique, not new, something new. It's old thing. It's called dot product. You learned that previously from other courses. It's also on your textbook, page 13. If you turn to page 13 on your textbook, and you will find out it says dot product. And I highly suggest you to read that part after class about dot product. Okay, so basically what dot product is whenever you use dot product, it projects the vector to a certain direction. That's what dot product does. So because we're looking for that V dot, remember V dot, it's the ET component of the acceleration equation under path coordinate system. So this is the equation under path coordinate system for acceleration. V dot, it's just the ET component. So by using dot product, we can actually just, by using the A times the direction of V dot, which is ET, that's a dot product. So this is the projection I'm talking about. Since V dot is only one component of this acceleration vector, we can use dot product velocity vector dot product that direction, which is ET, to find out what is the thing, the stuff in front of ET, which is V dot, what we're looking for. So in this problem, we want to find out V dot. We can use this method, the dot product, to find V dot. Another problem, what is ET? We don't really know the expression for ET or the direction for ET. So our next job is to find out ET, and we can figure out what is V dot. Okay. To find out ET, we need to use some of the given information. If we look at the velocity here, we do have the expression for velocity, which is this is a vector. Under path coordinate system, what's the equation for velocity? V equals what? You can tell me that. It's the equation for velocity under path coordinate system. Who can tell me what's the equation? Nobody knows? Just V times ET. Yeah. Yeah. By the way, remember, we have a quiz on Friday. The quiz covers chapter 1AB and chapter 1C. So pretty much all the stuff we learned in the last 2 weeks. So make sure you go back review it. No, we don't have cheat sheet for quiz. Okay, so the equation under path for velocity is just V times ET. Do we know V? Oh yeah, we know V. It's up there. We solved for V last time. Do we know this? This V, it's speed. Do we know that? We know the vector form of speed, which is a velocity. But do we know the speed of the particle? We don't know. It's not directly given to you for speed, but we can solve for that. Speed, in this case, since we already know the vector form of speed, so speed can be calculated by the magnitude of the velocity vector. This is our velocity vector. You can take the magnitude of this vector to get what is the speed of that particle, which is this component square plus this component square and square root. Okay, so we do know velocity, we do know speed. Can we find out ET? We have equation with only 3 variables here. We know this guy, we know this guy. Can we find out this guy? Oh yeah, we can do that. That's a simple calculation you learned from high school probably. You simply throw this V term to the other side of equation, right? Then you find out what is ET. So from here, we can find out ET. It's just V divided by this number V. Velocity V divided by this number V, which is speed. And since on the top, we have a vector, on the bottom, we have a scalar. What you need to do is just divide each component of that velocity vector with V. So here, that will give you what is ET. So use the first component divided by V, that's your ER, plus 4 plus 2 theta, theta dot divided by V, that's your E theta. That would tell us what is ET. Okay, I want you to compare, look at the expression for ET and compare that with the conversion equation we practiced multiple times. If we know the angle between two coordinate systems, we build triangles, and we can write ET equals some sine theta E R plus something cosine of sine theta E theta, right? But here, since we don't know that angle, we take a different route to get here. But eventually, your ET looks like something ER plus E theta. So it's a vector. ET still is a vector with two components. One is ER, one is E theta. Okay, now what's next? Now we know what is ET. We solved for ET. Remember? Yeah, now we can go back to here, to our ultimate goal to find what is V dot. Don't get lost. Yeah, oftentimes once we've done with this, a lot of you get lost. Okay, now what? Remember, the reason we want to have ET because we want to solve this. That's what we're looking for. So now we can do the dot product by using the velocity, the acceleration vector A, dot product ET. You will find out your V dot. One quick quiz here. In order to do dot product, you need to have two vectors. Vector, then you can do dot product. What's the result of a dot product? Would you get a scalar or vector? Yes, you will get a scalar. V dot is a scalar. Keep that in mind. That's just a number. Okay. Can you give you 2 minutes, 3 minutes? Plug in numbers to see if you can get a value for V dot. Let me know if you find the answer, a number for v dot. Even when I have theta and theta dot in this equation, but they're all given. Theta dot is given, and theta is also given as pi. Theta dot is constant, which is 3. Okay, I will just tell you what I have here. And, okay. I think the number, okay. For this case, what I end up with is v dot. It's a value that is greater than 0. You can double check that. So it's a positive number. If you end up with v dot, it's a positive number. That means the speed of p, it's increasing. Okay. You will, in your homework, there is a very similar problem. All right, anybody end up with a positive number for your v dot? Okay. All right. Any questions on this example? This is kind of the first techniques to deal with problems. You want to do the conversion, but you don't know angles. We use we use dot product. Okay, in the next example, we're gonna introduce different situation that you still want to do the conversion and you don't know angles. Okay, next example is on your textbook 1.C.2. All right, I want you to read that problem and set up given and find and think about how you solve that problem. So this problem looks like a 3D printer to me. Right, your particle P can moving. Our 3D printer has 3 axes. Here we only have 2. P. In this example, we're given the speed on x direction, y direction, and we also know this acceleration for VA and VB. We want to find out what is V dot and rho. Where do you see V dot and rho. That tells you what? V dot and rho, that's what? Path coordinate system, yes. And since we're in this section, we're dealing with conversion between coordinate systems. So of course, we need to have a path coordinate system here. What is another coordinate system you kind of want to use for this problem? Just look at how the problem is set up here. Cartesian, yes, we have something that is vertical, something that is horizontal. Cartesian, so this problem is pretty clear. We want to use both path and Cartesian. And we want to do the conversion between them, right? And if we look at the particle P, our Cartesian will be J and I. Our path coordinate system, how would you set up the path coordinate system? So can you imagine that particle P can only move along this slot and that slot? If B is moving that way, A is moving that way, can you imagine where is the particle P is moving? It's kind of moving in that direction, right? Somewhere over there, but we don't know exactly the angle. But we know particle P is moving towards to the lower right corner. What are the two unit vectors for path coordinate system again? E what? E T N. What's the direction for ET again? The direction of velocity of that particle. So ET would point into where that particle T is moving. And EN is pointing to the center of curvature. That's EN. And previously, I would just give you the setup of IJ, EN, ET and tell you the angle between them is theta, let you do the conversion, right? But now, we don't really know. We don't know what's the angle between them. That's called this angle right here. What is that angle? It's not given. We do not know. And this is another case that you want to do the conversion. You don't know the angle. So, but we can solve what is that angle for this case. And let's look at all the given condition here. Let's look at how the particle P is moving. Particle P, I'll just grab particle P here. P is moving along the ET direction, right? We know that on the vertical direction, particle P is moving at a speed VB. On the horizontal direction, particle P is moving at a speed of VA. And the resultant speed of that particle should go along this ET direction. And you can build a triangle. Let's draw a line here. So I'm just drawing a line that is parallel to VA. Now we're building this triangle right here with the hypotenuse. It's your V velocity vector of that particle P. We know both edges. One edge is VB, another edge is VA. Can we find the angle here? Can we find out the angle between the hypotenuse and VB? Let's call this angle right here. It's theta. How to find theta? So this is a triangle. We know the length of this edge. We know the length of this edge. What is angle here? Tangent, right? I heard tangent. Tangent theta equals this edge divided by that edge. Boom. We can find out what is theta in that case. So tangent theta equals VA divided by VB. You can use your calculator to find what is exactly the angle is. Angle equals tangent VA VB. All right, use your calculator to tell me what's the degree of angle. Do we have a number? 53. Okay, let's just use 53. That sounds about right. 53 degrees. All right, now we have this angle here, theta. All right, let's put this theta back to our coordinate system, right? All right, which one should I know this angle is theta. Right, if we come back here, which angle is theta? Is this angle theta? No, that's not theta. If you just assume that's the theta, no, we're wrong. The theta is the angle between the ET and that VB. VB is on vertical direction. So if you extend J, that angle right here is your theta. Now we know the theta. You know the drill. What to do next? Now you can follow the 6-step approach I told you. Build triangles to find converging equations. Okay, now you have 3 minutes to find out I equals something ET plus something E theta. All right, 3 minutes. Let's see who ends up the correct answer. Yeah, this conversion will be 100% on your quiz. Something similar. Okay, this is the answer I have. You can compare yours with mine. I simply this is theta, which is 53. So another angle right there is 37. You could end up with different form like what I have here. Since I use that 37 angle here, that's the answer you would have. If you use the 53 angle, you probably have sine 53 here and cosine 53 there. So everything is kind of reversed sine cosine. But make sure you use the right angle. Okay. Now we have this conversion equation. And just quick reminder, remember the table trick I told you guys? Once you have this set of equation ready, you can easily find out what is ET equals I plus J. What is EN equals I plus J. Remember that table? So once you build that table, when you try to find what is ET, you can just read that table vertically. ET equals this times I. So we have cosine 37 times I plus negative sine 37 point, that's J. For your EN, we have sine 37 and cosine 37. Okay, now we have our conversion equation ready. We can look at this problem. Okay, let's first look at this particle inside of the Cartesian coordinate system. Can we write out the velocity and acceleration for this particle under Cartesian coordinate system by using all the given information? All right, I want you to try 1 minute. It's very simple. Write out the Cartesian form of velocity and acceleration for this particle by using the given information. For your velocity, you have I and J components. One is vertical, another one is horizontal. Both velocity speed is given v and vb. That negative sign there for vb, it's because vb is moving to the negative direction of j. If you look at how we set up our coordinate system, j is pointing up, but vb is moving down. So that's why it's negative. Oops. For acceleration, that's just VA dot on I direction plus VB dot on J direction. Both VA dot, VB dot are given. Okay, next, since we are looking for what is VP dot and rho, that's from path coordinate system. You saw that two terms in the acceleration equation under path coordinate system. So let's write out, we don't know them, but we can write out the equation under path. That is V dot ET plus V squared over rho EN, right? Remember that? That looks familiar. So that's the acceleration of that particle under path coordinate system. And now we are given the acceleration of this part, the same particle under Cartesian coordinate system. Like we mentioned in section 1AB, we have three different ways, Cartesian, polar, and path, but they are all equivalent. Remember that? Equivalent. There are different language to describe the same thing. So now we want to look at how they're equivalent. We know this A equals 0.75I minus 0J as the acceleration of that particle. This is a path coordinate system acceleration of that same particle. Can I add an E cosine between them? There are both accelerations for the same particle. Yes. Even they look different. This one has I and J. That guy has ET and EN. They're just wearing a different clothes and hat. But underline, they're the same thing. So they're equal. They're equivalent. Let's put them together. V dot ET plus V squared over rho EN equals 0.75I minus 0J or plus 0J, doesn't matter. Okay, this is important. I want you to make sure everybody understands here. That's why we mentioned many times it is equivalent. No matter what coordinate system you are using to describe motion of a particle, they are all equivalent. But the only problem here is we have I and J on right-hand side of equation. We have ETN on left-hand side of equation. We can't really do anything when they have different unit vectors. We can't really solve for any unknowns. We're trying to solve V dot and rho, but we really can't do anything because they have different unit vectors. But what we just did at the very beginning, we have the conversion equations for ET, EN, I, and J's. Now your goal is to either plug in I and J or plug in ET, EN to make sure they're under the same coordinate system. Can you do that? Okay, that's all. How about let's put everything into something ETN. So get rid of I and J. Your goal is get rid of I and J, substitute I and J, so that everything will be ET and EN. Look at your conversion equations, substitute what is your I, what is your J. Okay. So what I simply just did is I replaced that I from your conversion equations by using cosine 37 ET plus sine 37 EN to replace that I. So this whole thing here is just our I. And once you put that 0.75 into this, then we end up with, on the right-hand side of equation, we end up with this guy times ET plus this guy times EN. Now when you compare, let's compare on both sides of equation. We have something ET plus something EN equals something ET plus something EN. Right? And it's an equal sign between them. That means everything, in order to make this equation valid, this number, V dot, has to equal to whatever is in front of Vt. So values in front of Vt should equal to values in front of Vt. Same thing for En. This whole thing should equal to whatever is in front of En. So now we can break, this is a vector equation with two components. We're going to use this again and again in this semester. We can always break down a vector equation to two scalar equations. So once you have that, next step is to write out the two components on ET direction. We can have an equation, a scalar equation that tells us V dot must equal to whatever is in front of ET 75 cosine 37. Look at this. I only take the values in front of unit vectors. Same deal for En. We have V squared over rho equals 0.75 sine 37 degrees. So you have two scalar equations. Are we good here? You can always break down a vector equation to two scalar equations. Now we have two scalar equations. We know we're trying to solve what is V dot. Wow, V dot is very obvious. 0.75 times cosine 37. You get V dot right away. That's one of your answers. And here on the bottom here, we want to find out what is rho. So through rho on this side, through this the other side of the equation to find out rho. From the first scalar equation, our V dot can be solved right away. 179 meters. Oops, sorry. That's speed. It's 0.6 meters per second square. And from our second scalar equation, rho can be solved by using V squared divided by 0.75 sine 37 degrees. What is that V over there? Should I plug in VA or VB as a value for V? Any answers? Yes. If you only plug in VA or VB as V, that's incorrect. V here, it's the speed of your particle. I think we just did that in the last example. The V over there, it's the magnitude of your velocity vector. In this case, it's just VA squared plus VB squared. That's how you find V. Once you find V, rho is, the value for rho is 0.139 meters. All right. So you would, and this is another example that you don't have the angles between two coordinate systems, that you can find the angles by looking at the velocity, the speed, to find the angle theta. Okay, that's all for today. And remember, homework due on Friday. Make sure you start from today.